So we want to find solutions to this guy, right? And we know it's a line, so we know that there are an infinite number of solutions, right? X and Y can be almost whatever they want. Except this particular question wants us to find integer solutions, which is harder than you would think to find, right? Like you'd say like, well, maybe when X is 1, Y would be 11Y is 13 minus 7, so Y would be 4 11ths. And you're like, well, darn it, anyway, that's not an integer. Crud. And you could keep trying and trying and trying, but it'd be kind of hard. So what we're going to do is use the Euclidean algorithm to do it. And the first step we're going to do is actually ignore that 13 for a second, and we're going to prove that the greatest common factor of 7 and 11 is 1. So we're going to, actually we're just going to find the GCF of 7 and 11. And so we can do that, it's not so bad. I'm going to say 11, 7 goes in there one time with 4 left over. Drag that down, kind of ditch that. 4 goes into 7 once with 3 left over. 3 goes into 4 once with 1 left over. Sometimes the arithmetic is the hardest part, yes? And so drag that down. 1 goes into 3 3 times with nothing left over. Finally hit my 0, so I can stop and back that up. And so 1 is the GCF of 7 and 11. So here's where we start to go do the backwards thing. And I want to write 1 as a linear combination of 7 and 11. So I'm just going to run this thing backwards. I'm going to say that 1 equals, and I'm going to shove this stuff over, 4 minus 3 times 1. And don't bother multiplying anything out. It's so tempting to say 1 equals 1 and then it'd be like, oh, yay, I'm done. But leave it in this form, because now we're going to back this up to 3 and replace the 3 with what it equals. So now I'm going to have 4 minus, and I'm going to replace the 3 with 7 minus 4, right? 7 minus 4 times 1 is that 3. And that makes sense, right? 3 is 7 minus 4. And that extra 1, I'm just going to carry everything down. A little lovely. But, so the 3 got replaced with 7 minus 4. Replace that. And so now our next step is to gather. So how many 4s have I got? Got 1 4 here and another 4 here. So I actually have 2 4s. And how many 7s do I have? Just the 1. So we've rewritten, we've gathered, we're going to do it again. So back up to this one, replace the 4 with what it equals. So I'm going to replace the 4 with what it equals. 4 is 11 minus 7. And then the rest of this will stay the same. So that was my 4. This is my 2. It's 7 times 1. And then we're going to gather this stuff here. So how many 11s do I have? Looks like I have 2 of those. And how many 7s do I have? I've got 2 of them here, 1 of them there, so 3 of them. And I can stop once I reach all the way up to the top, because now I have that 1 equals 11 times 2 minus 7 times 3. Believe it or not, that is what I wanted. So I'm going to write that up here and say 1. Actually, I'm going to just rearrange it. I'm going to say 11. 1 equals 11 times 2 minus 7 times 3 is what we just worked out. And you're like, okay, that's great. You can check it too, right? That's 22 minus 21. It's like, okay, yay, 1 equals 1. How does this help me? You want to compare it to this, right? The only I've got my 11 times something, and I've got my 7 times something. I kind of need a 13. And so I can make a 1 be 13 if I want, if I multiply both sides of the equation by 13. So then I'll have 13 equals, I'm going to keep the 11 because I want the 11. And 2 times 13 is 26. I'm going to keep the 7 because I want the 7. 3 times 13 is 39. So now if I compare this guy to what I want, right? 13 equals 7x plus 11y. Couldn't I rewrite this as a, let's see, couldn't I do 13 equals 11 times 26 plus 7 times negative 39? And that way you can see, you just sort of rearrange it, that your x is negative 39 and your y is the 26. So 7 times negative 39 plus 11 times 26 should give you 13. So we have lovely integer solutions. I don't think I would have stumbled across those had I just kept plugging in numbers to that. You can test it, throw it on a calculator, it'll work. Phew.
Wow, that was a good one.